Hello everyone, welcome to this NPTEL online certification course on material characterization. The title of the course is Scanning Electron Ion Probe Microscopy in Material Characterization. Myself Debabrata Pradhan, Associate Professor at Material Science Center, IIT Kharagpur. Today, I will mention three major microscopic techniques that will be covered in this course and the brief history on microscope development, magnification, the resolution of microscope and the lens aberration that play spoil shot to deteriorate the resolution. These are the topics we will discuss today. Let us go to three major microscopic technique that will be covered in this course. First will be scanning electron microscopy, then scanning ion microscopy, in particular helium ion microscope, then scanning probe microscopy. So, in each case I will be covering the basic principle, different parts and their functions, how signals are obtained using this technique and they are used for constructing images, how different parameters are varied to get the desired information and how samples are prepared to be examined under these microscopes. And all these microscopes provides us three dimensional images. Let us understand each word of this technique. First is microscope. Microscope word comes from the two Greek word, one is mikros that means small and another is scopian, to look at. So, an instrument or system that is used to view objects that are too small that we cannot see by naked eye is called microscope. And the science of investigating such small objects using the microscope is called microscopy. We visualize all the objects through our eye. Just mere presence of eye is enough to see an object. Just mere presence of eye may not be enough to see an object. For example, you are in a room painted with a black color paint in the wall and you switch off the light, window is closed, door is closed. So, there is complete darkness, let us say in the middle of the night. Can you see an object even though your eyes are present? You cannot see any object present in the room because of the darkness. So, light has to be there to get reflected from the object and pass through this space and reach your eyes. Once it reaches your eyes, then the signal is transferred to the brain and it allows us to detect the presence of an object, its appearance, its color and its shape and size. If we do not have light in the room, then we cannot see the objects. So, we can say that without light there is no sight. In addition to the presence of light, we must have an eye, that is what detector here. Therefore, we are able to see any object present in the room. However, as you know, light has a wavelength in the range of 400 nanometer to 700 nanometer. So, if an object is of size smaller than that, then this visible light will not enough to see an object of size less than the wavelength of the light. And there comes the electrons to rescue us. Electrons being a charged particle of very light mass can be passed through the space if we made it to vacuum, and we can change the wavelength of the electron to the desired value by changing its velocity. If we apply potential difference between two electrodes, then the velocity of the electrons will change, therefore, wavelength will change, and we can have wavelength much smaller than the wavelength of the light. And therefore, using the electron, we could able to see the objects of a much smaller size. Though the light microscopy is used extensively in pathological laboratory to see objects which are little bigger or in the range of the wavelength of the light, we extensively used electron microscope to see the objects of much smaller size that we cannot see by the light microscope. So, the middle word is electrons here. If we use electron beam to see an object, then that is called electron microscopy. We can also use ion. Ion electrons are all same, but ions can be different, and ions can penetrate less into a specimen as compared to the electron, because electron is much smaller in mass, smaller in size, that can penetrate much deeper into the sample as compared to the ions. So, the ions can provide us much superior quality images as compared to the electron microscopy. So, that is where ion microscopy come into the picture. And then we have probe microscopy. We were talking about that we are in the dark room and there was no presence of light, and we discussed that we cannot see an object if there is no light, but actually still you can know the presence of object in the room in the absence of light. How would you know the presence of light in the absence of light? How would you know the presence of an object in the absence of light? If you crawl around with your hand and legs, probably you can locate where a table is placed, and if you carefully touch by your hand, you can find if a sheet of paper is placed on the table, if there is a pen on the table, or if a tennis ball is there or cricket ball is there or a cone is there on the table, you can locate it using your hand and fingers. Even by touching the pen, you can tell whether the pen body is metallic or plastic. So, here the fingers in our hand acts as a probe to detect the presence of an object inside the dark room. So, it is always not necessary that light to be present. In the absence of light also, we can know the presence or absence of an object at a particular place. This is the middle one coming, that probe. So, if we use a physical probe like a blind man does, he uses his white cane to locate an object or something is close to him or her. Similarly, we can use physical probe to measure the size, shape of an object. So, here you see the middle word electron, ion, probe coming into picture of microscopy. Then the first word is our scanning. Scanning means running down or systematically moving a probe. It can be focused ion beam or focused electron beam on the surface of an object to produce an image. So, therefore, we say scanning. So, in this case what we do is that we use either electron or ion or probe to visualize an object or create an image to know its shape, size, morphology, etc. So, all these three techniques will gives us three-dimensional image. All these three techniques gives us three-dimensional image and in the nanometer scale, less than 1 nanometer. Then let us go to the history on microscope development. So, microscope is developed quite long back, first in 1590 Hans Janssen and his son Zachariah Janssen developed the first microscope. Then in the 17th century, early 17th century, Galileo first used the compound microscope. Then in the same 17th century, Leeuwenhoek used the microscope to study the bacteria and other microscopic creature. And then Robert Hooke used the compound microscope to visualize microorganisms, and he has published his book in Micrographia with the photographs hand sketched of the microorganisms. And in the 18th century, more developments occurred to the optical microscope, particularly on the lens and how to increase the magnification. And so far up to 18th century, scientists were particularly focusing on the optical microscope to see smaller size objects. Then the breakthrough on understanding the maximum resolution achieved came in 19th century, and how small object can be viewed by using the microscope was postulated in the 19th century. Then in the 20th century, a major alternative to the light microscope came. All these previous years we have optical microscope or light microscope. Then in the 20th century, the use of electron beam instead of light is used to create the image, and this use of electron beam could provide us much superior resolution in the nanometer scale. Now, coming to the 21st century, this present century, we have ion microscopes that has been commercialized in 2007, approximately within last 10 to 15 years, and at present there are about 100 such ion microscope. Whether those ion microscope could replace the electron microscope remain as a question, because ion microscope could certainly provide much superior resolution as compared to the electron microscope. We will see in this century, in next 30-40 years, how much of the electron microscope will be replaced by the ion microscope. Indeed, expert believes that both will be exist for next several couple of decades or next several decades, and they are unique in their own sense. In these slides, what you have seen, there is two important words: magnification and resolution. So, let us try to understand what is magnification and what is resolution. So, magnification is nothing but the ratio of image size to the object size. Theoretically, one can have an image of any size, and thus magnification can be of any value. But by increasing the magnification to any extent would produce the blurry image if the resolution is not good enough. So, just by increasing the magnification, if the resolution is not good, will not be enough. Then what is this resolution? It is defined as the closest spacing between 2 points that can be seen through a microscope as separate entities. Like if we have 2 spots here and I could see these as a separate entities, then I can say this is my resolution. Let us say I have another 2 points which are much more closer than this, then my resolution is even better. If these two spots are far away, then resolution is worse. So, resolution, this value, the spacing between two points or objects should be as small as possible. The value, if it is small, that means we have better resolution or higher resolution. So, first let us try to understand what is the resolving power of human eye. How small object our eye can see or detect. So, resolving power of a human eye. So, as per Rayleigh criteria, theta minimum, which is the angle of resolution or minimum angle of resolution, is 1.22 lambda by d. So, here theta minimum is the angular resolution, and lambda is the wavelength of light, and d is the diameter of light gathering element. Diameter of optical element, let us say objective lens. This angular resolution theta minimum can be converted to spatial resolution by multiplying with focal length f. So, we can write that del L is equal to theta minimum into f, where f is the distance between object and objective lens or our eye, and which is equal, then we can write which is equal to 1.22 f lambda by d. This is our angular, this is our spatial resolution. So, now if let us say if our eye is placed 1 meter away from an object, let us say f is 1 meter, let us say f is 1 meter, and say lambda is let us say green light 500 nanometer, and d is the detector, that is our eye. The let us say the diameter of our pupil in the eye is 4 millimeter, let us say 4 millimeter. Then we will have del L is equal to 1.22, then 1 meter we can write 1000 millimeter into 500 nanometer, then this is 4 millimeter, and that would give us around 0.15 millimeter. Remember, this is the diameter of pupil in the eye. So, our eye can detect objects placed as close as 0.15 millimeter. So, this is the resolving power of a human eye or resolution of a human eye. This is the resolution of a human eye, 0.15 millimeter. So, this again if let us say we can write again del L is nothing but d minimum, that is the minimum distance between two objects, is equal to 1.22 f lambda divided by d. Let us say we have a lens, and let us say its focal point is here, and then this is the angle of aperture alpha, and this is the optical lens, it is let us say diameter d, and here we can write, 10 alpha is equal to d by 2 into, this will be equal to d by 2 f. So, now I can put that here, which is equal to 1.22 f lambda divided by 2 f into 10 alpha, 2 f into 10 alpha. So, which is nothing but 0.61 lambda divided by 10 alpha. So, here alpha is angle of aperture, or we can say half angle of the cone of light from one of the object. So, then we can write this alpha is very small, actually this alpha is very small, which is equal to sin alpha, which is equal to 10 alpha, and we also have called refractive index of the medium between the lens, objective lens and the object. So, therefore, this d minimum is written can be written as 0.61 lambda divided by mu sin alpha. So, this is what, or we can write it which is equal to 0.61 lambda divided by N A. This is called Abbe's formula on resolution. This is called Abbe formula. This is reported in derived by Ernst Karl Abbe in 1870s, and this underlines the importance of lambda, that is wavelength of the light, and numerical aperture. Numerical aperture is mu sin alpha, here mu is the refractive index, where mu is the refractive index of the medium between the object and objective lens. So, as you see, this d minimum, that means minimum distance between two objects, is directly proportional to the wavelength of the light or wavelength of the any rays or electromagnetic radiation. So, having smaller the wavelength means we have d minimum smaller, that means good resolution. Otherwise, in order to decrease the value of d minimum, we should increase the value of refractive index and angle of aperture. So that is what we can do. So, now using a light, visible light, let us say we can use minimum 400 nanometer, and if we use UV light, then we can go ahead to use 200 nanometer of wavelength, and using that and if we use oil immersion lens, which has a little higher refractive index, at the same time if we use the larger angle of aperture or aperture angle, then we can have this numerical aperture using the oil immersion lens with a larger aperture. This numerical aperture value can go as high as 1.4 to 1.7, and with that value we can achieve a resolution of around 150 nanometer. So, let me clear this. We can have, like we had got formula, d minimum is equal to 0.61 lambda divided by mu sin alpha, using let us say ultraviolet light, let us say violet light of 400 nanometer and oil immersion lens, and with a large aperture, we can achieve d minimum is approximately 150 nanometer, which is good enough to see bacterial cells. This can be done using a optical microscope. However, we cannot see any object of smaller than this size using the visible light. So, for that we need the electromagnetic radiation or any particles which travels at a much faster rate with a smaller wavelength. Let us talk little more about the resolution. Resolving power. Okay, this go to next slide. Okay, let us talk about resolution. Even though lenses used in the microscope are perfect, resolution would be limited by the diffraction. Diffraction occurs when a wavefront is blocked or impeded by an object. As you see here, this almost parallel wavefront emerges as spherical wavefront after it passing through an aperture. This is due to the diffraction and interference. So, in any microscope, light has to pass through a series of aperture and lenses themselves, and therefore, they will undergo diffraction. So, the beam of light which is supposed to be seen as a perfect spot will no more be appearing as a perfect spot, rather than series of the cones with diminishing intensity from the center. That you see here, we have in the center that is called airy discs. Here, when light passes through a small aperture, instead of giving us a perfect spot, it gives a disc, and then around that there is a cones of or rings, which these rings are called airy rings, airy ring with diminishing intensity from the center. So, this is due to the diffraction. Now, if we, and this diameter of the disc, the diameter of this disc is inversely proportional to the aperture diameter. So, this diameter of the disc, let us say diameter of the disc is d, this diameter is inversely proportional to the aperture diameter. Now, if there is two spots or two aperture or maybe two objects from where diffraction occurs, if they are too close to each other, then they will not be resolved. They are almost overlapping on each other, and if these two spots are little away from each other, and this is what the resolve condition at which they are not overlapping each other, and as per the Lord-Rayleigh, when the maximum intensity of the airy disc coincide with the first minimum of the second, then we can say these 2 points are just resolved. This is what happens, the best condition of our resolving two objects. When the intensity, maximum intensity of an airy disc coincides with the first minimum of the second, then we can say these 2 points are just resolved. Is that only diffraction that spoils the resolution? No, we have several other aberrations too, and we will be discussing what are those aberrations in our next lecture. Thank you.